In this video, we're going to sort of continue our graphing discussion and specifically looking at some basic shapes that are not just lines. In our last example, we talked about some real basics of graphs, working with the coordinate system, and then we graphed a couple of linear equations. So I want to start with you with the graph of the basic quadratic, y equals x squared. So this is a quadratic equation in two variables. And while this is not the only technique that we will ever talk about, in this particular lesson, I want to discuss with you the approach of graphing by plotting points. So what do I mean by that? Well, you kind of saw it in our last lesson. What I mean is, and you'll see that sometimes it's handy to make a chart like the one that I'm making right now. We're going to try out some values of x and find matching values of y. So I'm going to use a different color for the x values because I'm going to pick all of them. And then based on the ones that I pick, I'm going to find my value for y. The reason that I'm doing this is that I have y expressed in terms of x. I think that's actually an important expression to be comfortable with. Y is written in terms of x. And when you have that, you won't always have it, but when you do, it makes it really, really clean to pick a value for x and just essentially kind of plug and chug to get the value for y. So while you are totally welcome and it's fine to pick some values for y and then solve for x from there, it would actually take some solving, right? Whereas if we just pick a bunch of values for x, it's essentially plug and chug to get the values for y. So it's a little easier to do it that way. Okay, so I'm going to pick a variety of values. We'll do -2 for x, -1, 0, 1, and 2. When you're graphing by plotting points, and when the equation is not linear, as it is in this case, there isn't a set number of points that you need. So what you're going to be looking for is you're going to be looking for some kind of a shape, some kind of a trend. And once you see that emerge, you've got enough points. Until you see it, keep plotting more points. So we've got 5 points happening here. That'll probably be enough. But if we needed to, we could plot more of them. Okay, so if x is -2, y is just x squared. So we're going to square -2 and we'll get 4. Now, I actually like to remind my students that a point is an ordered pair. So I'm going to write the point off to the side here. And I'm going to do that for every value. When x is -1, when we square -1, we get +1. So the point there is -1, 1. When we square 0, we just get 0. When we square 1, we also get 1. And when we square 2, we're back to 4. Okay? So let's plot these points and see if we're starting to see a shape. Now, what I'm sort of hoping is that you've encountered quadratics before at some point in your life. And so maybe, even if you don't remember what the shape is, as you start to see the points, it'll jog your memory and you'll say, oh, right, I remember now. That's the shape I'm looking for. So let's see what we see. So -2, 4 is there. If you want to label your points on your graph, you can. I'm going to skip that because I want to be really, really, really clean to be able to see the shape that's emerging. -1, 1, 0, 0, 1, 1, and 2, 4. Okay, so I have 5 points here. Now, some of you might be looking at that and saying, oh, right, there it is. This shape is called a parabola. And if you want to be really informal and sort of casual about it, you can say that it sort of looks like a U shape where the legs of the U are gradually opening wider and wider. Now, if you're looking at this and you're like, I don't see anything, that's when I meant you can plot more points if you want. So like you could have plotted -3, it would have been -3, 9 up here, 3, 9, that would have been up there. So, and you could have even done -1.5 if you wanted, -0.5. So you can plot as many points as you want. And frankly, I encourage you the first time or two that you're working with a new type of equation and graphing it for the first time, plot a lot of points until you really see that shape emerge. I'm going to go ahead and draw it in here. Now, remember, we only plotted these 5 points, and then we kind of saw what was happening, and we stopped. Oops. But we could have kept going, so it's really important to understand that this graph is not limited by the specific points that we plotted. Okay? So some people will tell you that you should be extra thorough about that and put arrows on the ends of your graph to indicate that it goes on forever. I'm not a big fan of arrows on tips of graphs. I think it kind of clutters the graph, but it's also not wrong to put them. So if you like them, then put them there. Okay, so that's one example. Let's look at one more quadratic example. So let's look at y equals x squared minus x. Okay, so this is still a quadratic. I want to make sure we understand that. And this time, I actually want to take sort of a different approach. We will plot some points, just random points, but I want to think about the intercepts of this graph, right? So one of the reasons I want to think about this is that I want to really ingrain you with the idea that intercepts are always the same thing. They are always the points where a graph crosses the coordinate axes. A graph may never cross the x-axis. It might cross it more than once. A graph may never cross the x-axis. It may cross it more, the y-axis. It may cross it more than once. So, but the theory is exactly the same each time. So let's look at the y-intercept. And then the x-intercept. And again, I'm kind of calling it x-int, y-int, but there could be more than one. So remember, we talked about this a little bit. Just going to sort of quickly review. If you're looking at the y-intercept, you're looking at a point on the y-axis. And that's a point that didn't move side to side from the origin, only up or down. So the y-intercept is any point whose x-coordinate is 0. So to find the y-intercept, we're going to set 0 for x and see what happens. Okay, so here goes. So we have y is equal to 0 squared minus 0. Oh, so that's just 0. So the y-intercept here is the origin, okay? So if you want, we could plot it, right? This is graphing by plotting points after all. Okay, now let's look at the x-intercept. So remember, x-intercepts, and I'm going to put like a little reminder dot here just to quickly review. X-intercepts are points on the x-axis. So those are points that only move side to side from the origin, not up and down. So x-intercepts are points that the y-coordinate is 0 and the x-coordinate is not, or is potentially something other than 0. So the way that we find the x-intercept is we set y to 0 and we solve for x. So this is a quadratic equation. And I hope that by now, you've had a little bit of experience with this so you can see, oh, look, you can factor x out on the right-hand side. So it becomes x times x minus 1 is equal to 0. And so this is possible when x is 0 or when x minus 1 is 0, which happens when x is 1. So we have two x-intercepts. One of them is the origin. We kind of already knew that since the origin was a y-intercept and the origin is on both axes. but we also have this other intercept at 1. Now, check it out. One thing that we don't talk about very much, but that's actually really quite important, is the idea of scale, right? So when we see graph paper like we have here, it's very easy to assume that we should use 1 square in the graph paper to mean 1 unit of length. But there's no reason to make that assumption. In fact, if you're going to have a really good graph, you should always mark the scale on it. So in fact, let me follow my own advice and go back to my graph earlier. So we can see that in the first graph, I let 1 square be 1 unit. In this graph, I'm actually going to go ahead and let 2 squares be 1 unit so that you can see some more nuance. So it's really up to you. Like, you could have just as easily made just 1 square be 1 unit, but I want to give you that notion. Okay, so we've got our intercepts plotted. Let's try a couple more points. Okay. So I'm going to do the same thing. In fact, let me do the x values in a different color. So we'll pick a point for x, pick a value for x, and then we'll kind of solve or plug for y. Now, I already have 0 and 1, so I'm going to do -1 to have a value to the left of 0. And you know what? I want to do 1/2. I want to look at what happens exactly halfway between my 2 intercepts, and then I want to look at 2. Okay, so 3 more points just to get a sense of shape. Okay, so if x is -1, we are plugging that in to x here. So we'll have -1 squared minus -1. -1 squared is 1, minus -1, the 2 minuses make a plus, so that's actually 2. So the point here is -1, 2. Okay. For 1/2, so don't shy away from trying fractional coordinates. They will happen, they will come up, and I think it's kind of important to try them. So 1/2, you'll have 1/2 squared minus 1/2. 1/2 squared is 1/4 minus 1/2. So 1/2 is 2/4. So this turns out to be x coordinate 1/2, y coordinate -1/4. And then last but not least, when x is 2, y squared is 2 squared minus 2, which is 4 minus 2, and that's back to 2. Like I've said before, you are welcome to plot more points. But my kind of basic advice is plot the ones that you start with, and then if you feel like you need more, then plot more. So kind of a gradual approach. Okay, so -1, 2. Don't forget that our scale is 2 squares per unit. So this is -1. Here's 1. Here's 2. So there is -1, 2. Now this is curious, right? This is like a real foray into the land of scale. So 1/2 is halfway between 0 and 1. Now you see why I use 2 squares for 1, right? Because now I have a nice neat measure for 1/2. And then -1/4. So don't forget, 1/4 is half of a half. So -1/4 is halfway down. Okay? And then 2 is back up to 2. So there is our shape. And remember, I'm going to write it again here just because I think there are never too few opportunities to write down the word that describes this shape. It's such a key shape. It's a parabola. Okay, so there you are. And again, we should really make it clear that this graph goes on forever. My graph bumps into my little chart there, so I'm going to go ahead and kind of stop it there and then put an arrow on it to indicate it keeps going. So this was two examples of quadratic equations and their graphs, and also a little bit about using point plotting to sketch graphs. I want to end this video by looking at two more shapes that we will be spending a lot of time with, and I'm not going to spend a bunch of time on each example. I'll quickly go through it because both of these are shapes that we will come back to many, many times. So the shape that I want to start with for our next example is this one. So this is, and I'm hopeful that this symbol is not totally new, but here we're talking about the absolute value of x, right? So we might take a brief moment to just remind ourselves that absolute value is defined by the distance from 0 if you were moving along the number line. So the kind of crucial thing about absolute value is that it is non-negative. You are never going to have a number whose absolute value is negative. It can be 0 and it can be positive, but it cannot be negative. All right, so here goes. Let's draw some axes. Oops. Okay, and then from there, we'll make our little chart. And actually, I kind of hope that in watching me do this example, you'll see why I made some of the decisions that I made in my first example. I'm going to do the same thing for the same reason. Here I have y expressed in terms of x again. So it's probably cleanest to just pick a few values of x and then solve for y. I'm going to pick the exact same values for x that I did for my very first example, y equals x squared. Now look though, what is the absolute value of, oops, I wanted to do that in a different color, excuse me. What is the absolute value of -2? Well, the absolute value of -2 is the number of units away from 0, right? So if you're like imagining yourself starting at 0 on the number line and then kind of walking to get to -2, you're going to take 2 steps. So the absolute value of -2 is 2. By that same token, the absolute value of -1 is 1. The absolute value of 0, well, that's just 0. The absolute value of 1 is 1 again. And the absolute value of 2 is 2. So I'm going to plot these points sort of nonchalantly. So there's 0, 0, 1, 1, 2, 2, 0, 0, -1, 1, and -2, 2. So if you look real quick at these 3 points, the one at -1, the one at 0, and the one at 1, they're all exactly the same as these 3 points. So a really interesting question is, like, how do you know if you've never encountered a quadratic or an absolute value before? How do you know that a quadratic has this beautiful kind of soft bend, whereas absolute value has this like really beautiful sharp corner? And so this is where the question of more points comes in. So say that you are in that predicament, that you haven't worked with these shapes before, and you are not convinced that the shape here is any different than the shape here. So that's where you could plot more points. You could say, well, let me look at what happens at -1/2 and +1/2, and let's look at it on both equations. And so that's where you would start to see that in the case of the parabola, you have a soft bend kind of like this, whereas here it's a sharp corner like so. So when I say you really can plot more points, as many points as your heart desires, I truly mean it. Okay, so here we are. All right, so that is the shape of the absolute value graph. So I won't call it a V shape because it does depend a little bit on what you have inside the absolute value. As long as what's inside the absolute value is linear, you will have that sort of V shape. But if you put something non-linear in there, it would no longer be a V. But I will say that one thing that is characteristic of the absolute value shape is that it has sharp corners. It's one of the rare graphs that we look at that actually has sharp corners in it. Most of the graphs we spend our time on do not have sharp corners. Okay, in your homework, you might encounter a problem, something like y equals the absolute value of x minus 2. So I invite you to try to kind of use all of the same techniques to stitch that together. And of course, if you have questions about it, feel free to ask them in discussions or office hours, whatever you would like. My last example, is the square root graph. So this is another one of those shapes that we'll actually spend quite a bit of time with. So I figured we would take a look at it. This one's kind of interesting. Yeah, that's not very attractive. Let's try again. So this one is kind of interesting because for our first 3 examples, when we were plotting points, like we did here, we did so basically indiscriminately. We picked whatever values we felt like for x, and we figured out what the value for y would be stemming from that. Now here, though, you might already be on the same page with me. It doesn't work to take negative values of x. The square root of x is only defined as a real number if the radicand, the number underneath the square root, is positive. So if you want to take the square root of -5, that's totally possible, and we'll talk about how that works later, but it's no longer a real number. And our graph is only capable of showing us real numbers. So when I go to pick my values for x, I'm only going to use reals. And to make life a little bit easier on myself, I'm going to use perfect squares. So I'm going to use 0, 1, 4, and also 9, just to see what it becomes. All right, so what do we have here? The square root of 0. The square root of 0 is 0, so this graph goes through the origin. The square root of 1 is 1. So a really common question here is, wait a minute, how come it's not plus or minus 1? And so that's where we need to remember that the square root, by definition, is only the positive number whose square is what's inside. If you were looking at the equation x squared equals 1, that's the positive or negative square root of 1. So there is such a thing as the negative square root of 1, which is -1, but the square root of 1 by itself is just +1. If you have more questions about that, feel free to ask in office hours. The square root of 4, by that exact same token, is 2. So we have the point 42, and the square root of 9 is 3. So that's 9, 3. Okay, so off we go. So here is 0, 0. Here is 1, 1. 4, 2. And then 9, 3. Okay, so again, if this is a new shape for you and you're not really seeing anything, you're welcome to plot more. Now, I specifically avoided numbers that weren't perfect squares here because I wanted to keep my graph neat. But if you feel like it, you are welcome to try something between 1 and 4, like 2. And you'd see that the square root of 2 is about 1.4, not quite up to 1.5. The square root of 3 is not quite up to 2, it's about 1.7, right? So you are welcome to plot more points if you like, if it helps you flesh the shape out a little bit better. But I'm going to go ahead and draw the shape in. So a couple of things to notice here. Notice that the graph does not end at the last point we plotted. It keeps going, and it's important to show that. And second, notice how the graph starts at the y-axis. There is nothing happening to the left of the y-axis. Like this whole section, there's just nothing happening there. So there is no guarantee for any given graph that it occupies all 4 of the quadrants. Case in point, our previous example doesn't have anything in the bottom 2 quadrants. Now, the last thing that I want to tell you before we move on is I want you to notice the interesting overlap between this shape and the shape of a quadratic, the parabola. Okay, so that is not an accident. In fact, what you're going to notice is that square root equations, the shape is half of a parabola on its side. So right now we don't quite have the machinery to understand why that would be, but it is not a coincidence. It doesn't just look like half of a parabola. It actually is half a parabola. And every square root, if you have the square root of something equals y, the graph of that is going to look like half of a parabola for our purposes. So of course you could get creative and you could look at some funky radicals, but for our purposes you'll kind of grow to see that connection. Half of a parabola is the graph of a square root equation. All right, everyone, so this is our last video for this first module. It was a big module because we needed to set up quite a few basic foundational ideas. I think you'll find that the next module is maybe a little bit lighter. So thanks for your hard work this week, and I'll see you next week. Bye.